Hello, welcome back to Chapter 7. We're going to continue with System of Equations, and today we're covering 7.3, which is multivariable linear systems. So don't be afraid of it. It just means that there's one more variable, and that's fine. So what's our objective? Our objective is to use back substitution, to solve linear systems in row echelon form, to use Gaussian elimination to solve systems of linear equations, to solve non-square systems of linear equations, and then to use systems of linear equations in 3 or more variables to model and solve problems. Okay, so first of all, what is row echelon form and back substitution? Like, what is that? Okay, so the method of elimination, you know how we've done elimination where we apply, we do a system of linear equations for 2 variables, but actually the method of elimination adapts to computer use for solving many variables. But when we use this method, the goal is to write the system in a way that you can do back substitution or substitute back into previous. So let's see what we're trying to talk about here. So let's see here. Here's an example. We have x minus 2y plus 3z is equal to 9. Then we have a negative x plus 3y is equal to negative 4. And then we have finally 2x minus 5y plus 5z is equal to 17. So that is a system of 3 linear equations in 3 variables. Now if I take this system and I write it, I write it in order, like I write, 3y, 3y plus x is less than 4, or if I manipulate the system around and do some solving, like if I was to, I don't know, I was to add together a certain amount, and I would get to where z is equal to 2, and I would have, I could have the expression y plus 3z is 5. So this is an equivalent system, and basically, let me just tell you, notice the way that it is. Like the top one is the largest one, it has all 3 variables and then the equal sign. And then the middle row has only 2 variables, and then the final row has 1 variable. So it's kind of like a triangle pointing downwards-ish, if you use your imagination, yeah? So that's kind of, that's what row echelon form is basically. It goes from largest to smallest. And it has like a stair-step pattern with leading coefficients of 1, okay? So if you have a system in row echelon form, it's very easy to solve after that because you just substitute back into the previous and so on. So let's see here. So let me show you what I mean. If I have this equation, x minus 2y plus 3z is equal to 9, y plus 3z is equal to 5, and then z is equal to 2. So what I can do is I can take the 2 and plug it back into the equation preceding it, right? So from equation 3, I know that z is 2, so I plug that back into equation 2, and I get y plus 3 times 2 is equal to 5, and solving for y, I get negative 1. Then I take negative 1 and z equals 2, and I put them both back into equation 1, and then I can solve for x. Okay, so then I have x equals 1, y equals negative 1, and z equals 2, which can be written as this, what we call an ordered triple. So you have parenthesis 1 comma negative 1 comma 2. Okay, next, Gaussian elimination. So 2 systems of equations are equivalent when they have the same set of solutions. So if you want to solve a system that is not in row echelon form, you can convert it to a equivalent system of linear that's row echelon form by using these operations. So okay, so how do we get equivalent systems? So let's see here. Basically this is a couple of things that we can do to get our system of equations into row echelon form. So we can interchange 2 equations, we can multiply one of the equations by a non-zero constant, we can add a multiple of one of the equations to another equation to replace that former equation. So it's basically like we're using elimination basically, right? It's, we already know how to do that, but we're eliminating x, we're eliminating y, Okay, here. So we rewrite, rewriting the system of linear equations in row echelon form usually involves a chain of systems where where basically we do what we just talked about, okay? And this process is called Gaussian elimination after Carl Gauss. Okay, example 2, let's solve the system of linear equations. So we have here 3x minus 2y is equal to negative 1, and then we have x minus y is equal to 0. So the first thing that we can do here is let's go ahead and write the x minus 1 on the top and then the 3x minus 2y equal to negative 1 on the bottom. Because it really doesn't, we really didn't really need to do that, but okay. I guess, yeah, it's the easiest way. So, okay, so we do that, and then let's multiply the top equation by negative 3. So the top equation is now negative 3x plus 3y equal to 0, and the bottom equation is still 3x minus 2y is equal to negative 1. So then, now we add these together, right? We're eliminating. So then you get the x's cancel out, and you get 3 minus 2, which is a y, which is really nice. And then 0 minus 1 is negative 1. So now the two equations you have left, you can have x minus y is equal to 0 on the top, and then y is equal to negative 1. Okay, and then if we plug in negative 1 in the previous one, right, we get x is equal to negative 1, and that's our solution. Okay, so let's see here. Let's do another one where we have more variables. So we have x minus 2y plus 3z is equal to 9. Negative x plus 3y is equal to negative 4. 2x minus 5y plus 5z is equal to 17. Because the leading coefficient of the first equation is 1, let's keep the x in the upper left position and let's eliminate the other x terms from the first column. So we have equation 1 and equation 2, and let's add them. And then we get y plus 3z is equal to 5. So then if we do that, we can rewrite this, right? So we added 2 together, we replaced it, right? The new second equation, we added the first to second, and then we got this new one, okay? And what can we do to get, what if we multiply equation 1 by negative 2 and add it to equation 3? So here is negative 2 times equation 1 on the top, so you get negative 2x plus 4y minus 6z is equal to negative 18. And on the bottom, equation 3 is 2x minus 5y plus 5z is equal to 17. So you add them together, you get negative y minus z is equal to negative 1. So then we add this to negative 2 times the first equation to a third equation, produce that new third equation, which is negative y minus z is equal to negative 1. So we've eliminated everything but the x in the upper position of the first column. We work on the second column. So basically, look, the first column, there's only this x. So now we need to get rid of y, So we add the second and the third equation. So if we were to add these two together right here on the top, notice the y's would cancel out and you would get 3z minus z, which is 2z, and then 5 plus negative 1 is equal to 4. Okay, so now you have that z is equal to 2. So look, now you have a coefficient of 1 for z, so we divide by 2 or multiply by 1.5, same thing. And then this is it. So we have our example 1 system. This is the same thing. Okay, so that's where we get 1, negative 1, and 2. Okay, so what's actually happening when we're doing Gaussian elimination? Like graphically speaking, like what is that, So if we have a linear system, meaning that all the variables have an exponent of 1, that means that these are the possibilities. You either have one solution, you either have infinitely many solutions, or you have no solution at all. And so we know that a system of 2 linear equations and 2 variables, we can do that as lines that are intersecting, coincident, or parallel, meaning that they cross or they don't cross, right? They cross all the time. Well, in this case, here we have a system of 3 linear equations in 3 variables, and it has a similar graphical representation because an equation with 3 variables, it's 3-dimensional, right? So it describes a plane. Okay, just like how 2 variables describes a line, a plane is described with 3 variables. So what's a plane? Remember, it's like a flat surface. It's just like an area extends out into infinity. Okay, so here in this case, figure 7.9, you can see that the 3 planes are intersecting at exactly 1 point. They all meet, and that's the solution. Okay, figure 7.10, the solution is an entire line because they all intersect at this line. And 7.11 would be when they're all the same equation, so the solution would just be one plane. 7.12, notice that they intersect like with each other, but not all together, right? Not all 3 at once, like 2 of them at a time. So this is no solution. And this is another case of no solution where you have the 3 parallel planes. Okay, so you either have exactly one solution, infinitely many, or no solution. Okay, that is our okay, so example 5 is a situation where you can have infinitely many solutions. So let's say we have here x plus y minus 3z is equal to negative 1, y minus z is equal to 0, and negative x plus 2y is equal to 1. So what if we took equation 1 and added it to equation 3? Okay, so if we did that and replaced the third equation, we would get 3y minus 3z is equal to 0. Okay, now what if we added these two, equation 2 and equation 3, but first we multiplied equation 2 by a negative 3. Okay, what would happen? So if I multiply equation 2 by negative 3, I would get negative 3y plus 3z is equal to 0, right? And when I add them together, I would get 0 is equal to 0. Well, what the heck is that? Well, if you have 0 is equal to 0, that's a true statement. It's always true. There's infinitely many solutions. And if you let, so let's say we want to express one of the solutions, okay? So we could do, if we let z equals a, where a could be a real number, we could use that system to find expressions for each variable. So for example, so if z is equal to a, and we solve for y, we would get that y is also a, okay? And if we plug that back into the first equation, so it'd be x plus a minus 3a is equal to negative 1, and we solve for x, we would get here 2a minus 1, a, and then a, and that would be a solution to the system. But it could be anything, so it's infinitely many solutions. Okay. Non-square systems. Okay, so far, each system of linear equations that we've looked at has been squared. What does that mean? That means that the number of equations is equal to the number of variables. So, for example, 2 equations, 2 variables. 3 equations, 3 variables. And in a non-square system, the number of equations differs from the number of variables, okay? So what's up with that? So what that means is if you can't have a unique solution unless there are at least as many equations as there are variables in the system. Okay, so let me show you what would happen. Okay, so here we go. So suppose you have these 2 equations, x minus 2y plus z is equal to 2, and 2x minus y minus z is equal to 1, okay? And we want to write this in row echelon form. So we have here, let's add, multiply negative 2 times the first equation and add it to the second. We cancel out the x's. We would get 3y minus 3z is equal to negative 3. And if we divide everything by negative 3 or just by 3, you get y minus z is equal to negative 1, right? So now if we let y equal, so if we solve for y in terms of z, we would get y is equal to z minus 1. And if we take that and we plug it back into the first equation, and instead of y, we put z minus 1, you would get x times, x minus 2 times the quantity z minus 1 plus z is equal to 2. You distribute that negative 2 and then solve for x, you would get z is equal to x, actually. So then we would do the same trick that we did before where we let z is equal to a and then write the other ones in terms of a. So then you would have x is equal to a, y is equal to a minus 1, and z is equal to a. So then you would say, okay, every ordered triple, what does that mean? Value x, y, z. So a point in space, that has this form would be a solution to that system. Okay, so it's not unique. It's not a unique solution. It's many solutions. Okay. All right. So for this last example, you could try to choose some values of a, and you can see that would produce these different solutions. So let's say if you let a is equal to 1, you would get 1, 0, 1. If you let a equal to 2, you would get 2, 1, 2, and so on, right? You could pick it as many as you want. And because a represents all the numbers, so all real numbers. And then to check it, you could plug either one of these back into the equation. You'll see that it would work. So pretty cool. Okay, so finally, we're going to talk about an application of system of equations. So let's see here we have this example, vertical motion. So let's say here we have the height of time t of an object that's moving in a vertical line with constant acceleration a is given by this position equation, where you have s is equal to 1/2 at squared plus initial velocity v sub 0, that's what that means, t plus s sub 0 initial height, where s is the height in feet, a is the acceleration in feet per second squared, and t is the time in seconds, v is the initial velocity at t is equal to 0, and s sub 0 is the initial height. Okay, so let's see if we wanted to find the values of a, v naught, and s naught when s is 52 at t equal 1, s is 52 at t equals 2, and s is 20 at t equals 3, and then let's interpret the results. So basically, here's the picture, okay? So this picture is great. So when t is 0, I guess that's when it gets thrown up, the item. I don't even remember what it was, but it's just an object, I think. Okay, so yeah, so t is 0, let's say it's initially at like 18 or what was it? Something, I forget. T is 20. So at t is equal to 3, it comes back. So let's say it's initially at 20 also, I guess. And then it goes up. After 1 second, you have 52, okay? Then it goes around. So actually, when you throw stuff in the air, it comes back down. We know that that's gravity. So that's kind of what's happening here. And then you have 1 second after that, it comes back to a height of 52. And then finally, after 3 seconds, it goes down to 20, and then before hitting the ground. So let's just basically, what you do is just plug these into the three equations. So you have t equals 1, 2, 3, and we have a value of s. So we have 1/2 a times 1 squared plus v naught times 1 plus s naught is equal to 52. Okay, so if you simplify this, multiply everything by 2, you get a plus 2 v naught plus 2 s naught is equal to 104, which is also incorrect, I guess. But notice this, okay, before we continue, notice that it's a, v naught, s naught, okay? So that's just 3 different variables. Might as well be x, y, z, okay? So we've been only doing x, y, z, but now in this case, we have an a, v naught, and s naught. Okay, finally, we plug in the second thing that they gave us, t is equal to 2, into the equation, the original equation, and you solve that, and you get this relationship. After multiplying by 2, we get 2a plus 2v naught plus s naught is equal to 52. And then when t is equal to 3, we get 1/2 a 3 squared plus v naught times 3 plus s naught is equal to 20. And we get, and after multiplying by 2, of course, we get 9a plus 6v naught plus 2s naught is equal to 40. Okay, so now you have this system of linear equations, right? So we just basically rewrote this, and there it is. It's nice and square, right? Because there's 3 equations and 3 unknowns. So how we solve it, well, of course, we can use Gaussian elimination. Okay, so if we take the first one, multiply by 2, add to the second one, and you get this. Negative 2v naught minus 3s naught is equal to negative 156. So you can try this out on your own, okay? So starting with the original, multiply the first one times negative 2, add them together, and then replace the second one, okay? And then finally, here, let's take this first equation again, negative 9 times, multiplied by negative 9, and then add it to the third one. So notice that the third one has this 9a. So the goal is to eliminate the a term. So we do that, and we get here this second equation, this third equation, negative 12v naught minus 16s naught minus 896. And then, you could probably simplify this, but that's okay. So then we take the second equation, negative 2v naught minus 3s naught equals negative 156, and we multiply it by negative 6 and add it to the third, you would finally get 2s naught is equal to 40. So that gives us s naught, right? Or s sub o, s sub 0, I guess. Okay, so now we have the form that we want. We have 3 variables. Actually, before we do that, we have here s naught is equal to 20, and if we multiply the second equation by negative 1/2, we simplify it and we get a coefficient of 1 for the second equation. So see how it makes that triangle. You have everything here. A has a coefficient of 1, B naught has a coefficient of 1, S naught has a coefficient of 1. And in order to finish solving this, we would just substitute backwards, right? So we would take this S naught, plug it into the second equation, multiply by 3/2, right? Subtract from both sides. And then we would take that V naught and that S naught and plug it into the first equation and solve for A naught. So then the solution would be A is negative 32, V naught is 48, and S naught is 20, which could be written as negative 32, comma 48, comma 20. Okay, so what does that mean? So if I plug that back in, I would get S is equal to negative 16t squared plus 48t plus 20. So that's your position equation, and that means that the object was thrown upward at a velocity of 48 feet per second from a height of 20 feet, because that's what the V sub naught represented and what S sub naught represents. Okay, that is it. 7.3, your homework is 1 through 39 odd. Okay, that's it for me, and I will see you on the next video.